So in section 5, we're going to show you that if you're given the mass percentage of the elements in a compound, one can deduce what the empirical formula is for the compound. So the problem might look something like this. If you only have 3 elements, carbon, hydrogen, and oxygen, and you decompose your compound into these 3 elements, you can determine the mass percentages. With that information, you can determine the empirical formula, and that can be used as evidence for the purity of your compound. Now, when we look at this information right here, these are representing mass ratios between the 3 different elements. But our formula, our empirical formula, is the smallest integer ratio or number ratio of the 3 different elements. So what we need to do here is re-express these mass ratios into number ratios. And a convenient place to start, since our mass ratio information is already expressed in percent or parts per hundred, is that if we assume we've got 100 grams of compound and we decomposed all of it, we would get 44.77 grams of carbon, 7.52 grams of hydrogen, and 47.71 grams of oxygen. So that, assuming 100 grams of compound, makes this a very convenient place to start our calculation. So then, if we assume that we have 100 grams of sample and we decompose it into their constituent elements, we're going to get 44.77 grams of carbon, 7.52 grams of hydrogen, and 47.71 grams of oxygen. So to get to our empirical formula, which is a number ratio of the elements, we need to convert all of these masses to moles. So we do that in the usual fashion, using the molar masses for carbon, hydrogen, and oxygen respectively as conversion factors. Plugging these values into our calculator, we now have the following number ratios in our formula. So we could write a formula with these numbers, but is this the correct empirical formula? No, because the empirical formula describes the simplest integer ratio, right? So how can we go about getting the simplest integer ratio? Well, there are 2 things that you need to do. First of all, we can look at our numbers here and recognize that any multiplication or division operation that we do on one number, say this one, then as long as we do it on the other 2, we are going to maintain our number ratio. Nothing will have changed. So if we just look at the smallest value, if we divide by the smallest value, we're definitely going to get an integer. That'll be 1. So if we divide them all by the smallest value, we may get integers for all of them. So that's step 1. Step 2 is that if you don't get integers, say in these 2 cases, you'll get some sort of fraction, and you'll need to multiply by some integer to get rid of the fraction. And of course, when you do that multiplication, you're going to need to do it for all of the numbers to maintain the number ratio. So let's see how this works. So here are, again, the number ratios that we generated already. And if we divide all 3 numbers now by the smallest, we get an integer here for the number of moles of oxygen. It's 1. Here we don't. Here we get fractions. So what we need to do here is convert these to integers. And all you really need to do, folks, here is convert your decimals to complex fractions. 1.25 is the same thing as 5 divided by 4, or 5/4. 2.5 is the same thing as 5 divided by 2, or 5/2. So we have 5/4, 5/2, and 1. So to get rid of the fractions, if we multiply all of our numbers by 4, 5/4 becomes 5/4 times 4 is 5, 5 halves times 4 is 10, and 1 times 4 is just 4. So now we have our formula with integers. Our empirical formula is C5H10O4.